Hi everyone! In this video we are going to continue from section 2.8, which is the star-delta equivalence. There could be some circuits in which some loads are connected in delta, while others are connected in star. In that situation, it is sometimes useful to express all the impedances as if they were connected, all of them in delta or in star. That is the purpose of the star-delta equivalence. So there, the line impedances can be obtained from the phase impedances as follows. You need to do the sum of all the combinations of the products in the numerator divided by the impedance of the branch connected to the node which is opposite from set I. So there you have, for example, for obtaining line impedance A, which is here, you have to do all the possible products of the phase impedances here, Z1 by Z2, Z2 by Z3, and Z3 by Z1, over the impedance of the branch which is connected to the opposite node. That is, if we are trying to obtain the line impedance ZA, the impedance which is connected to the opposite node is Z1. That is why you have here Z1 in the denominator. Analogously, you could do the same for obtaining line impedances B and C. In this way, if you have one load which is connected in a star and you want to transform that load as if it were connected in delta, then you can use these expressions here. On the other hand, we can have a load which is connected in delta and we want to transform that load as if it were connected in a star. Then the phase impedances can be obtained from the line impedances as follows. On the numerator you have the product of the two line impedances which have a common vertex on the phase impedance. And in the denominator you have the sum of the three impedances of the delta. Here you have the expressions. So phase impedance 1 could be obtained as the products of line impedances B and C. Let's go back. Here you have impedance 1, which are the two line impedances which have a common vertex, B and C. So that is why you have here the product of B and C, and divided by the sum of all the three impedances of the delta, the three line impedances. So you can do the same for obtaining phase impedances 2 and 3. Well, these formulas are useful when you have a load which is unbalanced, because in that case the values of the three phase impedances 1, 2 and 3 or the values of the three line impedances A, B and C could be different. However, if you have a balanced load, that means that the three phase impedances or the three line impedances, they have the same value. That means same absolute value and same angle. In that situation, the formula could be transformed to this expression, which is much more simpler, in which you have the impedance connected in a star is going to be equal to the impedance connected in delta divided by 3. Analogously, the impedance connected in delta would be 3 times the impedance connected in a star. So, when our system is balanced, we can simplify the previous expressions and we can use this expression here. In section 2.9, we are going to talk about power in three-phase circuits. So, in three-phase circuits, we can also apply the Boucherot theorem, but in that case, we will need to apply the Boucherot theorem to each of the phases of the system. So, a total active power, P, is going to be the sum of the active powers consumed by each of the phases of the load. So then you can have this expression. So UK will be the effective value of voltage on phase K. IK would be the effective value of current on phase K, and cosine of phi is the power factor of phase K. We can do the same for obtaining the reactive power Q. So here we will have this expression. Remember that the units will be watts in the active power and voltamperes reactive in the reactive power. So if we want the apparent power, which is the modulus of the complex apparent power, then we will need to use this expression. So this expression here is the complex power. As you know, the complex power is a phasor whose real part is the active power and whose imaginary part is the reactive power. So that is the same as 3 times the phase voltage multiplied by the conjugate of the line current, and this for each of the phases. That is why you have 3 times, because we suppose that the system is balanced and symmetrical, and then the powers are going to be the same for each of the phases of the 3-phase system. If you introduce here in the phase voltage UA the Ohm's law, you're gonna get the impedance multiplied by the current. So then you can transform this expression into this other expression, which is totally equivalent, which is 3 times the impedance multiplied by the absolute value of the current to the square. Both expressions, they give a phasor, which is the complex power in voltamps. Obviously, if you want the apparent power, which is the absolute value of the complex power, you can do a square root of p to the square plus q to the square if you have these two components, or on the other hand, you can multiply 3 times the absolute value of the phase voltage by the absolute value of the line voltage. You can also do a square root of 3 multiplied by the line voltage in absolute value and multiplied by the phase current in absolute value. All these expressions, they are equivalent. So in one particular problem, depending on the information that you have in the statement, you are going to use one of these expressions that you have here. We said at the beginning of this lesson that in 3-phase systems the instantaneous power has a constant value which does not depend on time, and that was an advantage in contrast to the situation that we had in single-phase systems where the instantaneous power was a sinusoidal wave that varied over time. So here we have the demonstration of that, which is quite important. So the total instant power is going to be the sum of the instantaneous powers in the 3 phases of the system. So here you have the sinusoidal wave, depending on time, for the power of P1, P2, and P3. As the system is balanced and symmetrical, the values of the voltages and currents here, in these 3 terms, they should be equal, they should be the same. So we can extract them from the expression, and then we will have the sum of the products of cosines here, okay? The sum of these 3 components which have the products of 2 cosines, each of them. If you remember some trigonometric relationships of products and cosines, then you can change the previous expressions to the following ones. And there you can see that the cosine of phi is 3 times here. So if you continue applying some trigonometric relationships, you are going to get to this expression here. And you can see that these terms that depend on time are going to be equal to 0. So at the end, we will have an expression for the active power, which does not depend on time, and it's constant over time. So this is a very important characteristic of three-phase systems that you need to remember. We can do something totally analogous with the reactive power, but in that situation, instead of cosines, you are going to have sines of the angles. And you will get to this expression here. So as you can see, you can calculate the active power as 3 times the absolute value of the phase voltage multiplied by the absolute value of the line current and multiplied by the cosine of phi. Or on the other hand, you can do square root of 3 multiplied by the line voltage and the phase current, and after that the cosine of phi. All this expression is also equivalent as 3 times the resistance multiplied by the square of the line current. So depending on if we have voltages and currents or we have impedances and then we have the real and imaginary part of the impedance, the resistance and reactance of the impedance, depending on the information that we have in the problem, we can use each of these 3 expressions here. In this section 2.10, power metering in three-phase circuits, we talk about how could we measure the power in these systems. And power metering in these systems is not trivial. The Blondel theorem states that the necessary number of wattmeters is usually 1 less than the number of conductors. That means that in the cases where we have the 3 phases and the neutral conductor, as we have 4 cables, we are going to need 3 wattmeters to measure power. And in that case, the total active or reactive power is going to be the sum of the active or reactive power measured by the 3 wattmeters. So for example, the total active power would be P1 plus P2 plus P3, while we should measure the reactive power to have the value of the total reactive power. So if the system is balanced and the load is symmetrical and also balanced, then we can have only 1 wattmeter, because the total power would be 3 times the power measured by that wattmeter. So in that case, we can use a single wattmeter. On the other hand, if we have a system with only 3 cables, that is, without neutral, we can use the Aaron connection. So in the Aaron connection, we only need 2 wattmeters. Here you have a phasor representation of phase and line voltages, and you also have the line currents and the angles among them. So according to the Blondel theorem, the total active power is going to be the sum of the active powers measured by the 2 meters. So the total active power is going to be P1 plus P2. While if we want to measure the reactive power, then we will need to replace the wattmeters by reactive meters. But that is if our system is a general system in which the load is not balanced. But if the load is balanced, then we can obtain the reactive power from P1 and P2. And the explanation would be this one. So P1 is going to be the real part of the product of the line voltage UAC multiplied by the conjugate of the line current A. The real part of that product will be the line voltage UAC multiplied by the line current and the cosine of the angle of that product. So if you pay attention here to UAC, its angle is minus 30. So that is minus pi divided by 6. And IA, its angle here is phi, minus phi. So the product, as we have a conjugate here, the product would be minus pi 1 plus phi, if you do the product of this, okay? So we would have minus pi divided by 6 plus phi. But as you know, the cosine of one angle is going to be the same as the cosine of the opposite angle. So that's why we can change from minus pi divided by 6 plus phi to this value here. For obtaining P2, then we will need the real part of the product of the line voltage BC multiplied by the conjugate of the line current P. So if you go back to the phasor diagram in the previous slide, there you can see that you are going to get the opposite of this angle, okay? And as the cosines have the same value for opposite angles, then you can change to this one. So we have said that the total active power measured should be the sum of P1 plus P2. If the system is symmetrical and all the line voltages they have the same absolute value, then you can extract this product of the line voltage and line current here in this expression. Then you can substitute here this sum of cosines by this product. And as the cosine of pi divided by 6 is square root of 3 divided by 2, at the end you will get to this expression. So P, the total active power, would be square root of 3 multiplied by the line voltage and line current and the cosine of the angle. If you do the difference over P1 and P2, then we will have this, and the difference of these two cosines will be 2 times the sine of pi over 6 multiplied by the sine of phi. So as the sine of pi over 6 is 1/2, then you will have this expression. So the consequence of these demonstrations that we have seen is that the sum of P1 and P2 is directly the total active power, because here we have get to this result, which was the value of the active power if you go back a couple of slides in this presentation. And the difference between P1 and P2, which were the measurements of the two wattmeters, is this one. And if you multiply by a square root of 3, there you have exactly the value of the reactive power. So when we have a balanced three-phase system with only 3 cables, we can use the iron connection and use only 2 wattmeters, and then we can obtain the total active power as the sum of the 2 measurements and the total reactive power as square root of 3 multiplied by the difference of the 2 measurements. With this, now we can solve example 3.
Hi everyone! In this video we are going to explain example 3 from lesson 2. So what do we have in this system? Okay, we have 3 loads whose impedance is Z1, which have delta connection. About these loads, we know that the total active power is 30 kilowatts and the power factor is equal to 1. Here we have another load in star connection. There we know that their impedance is Z2 and their active power is 500 watts and their power factor is 0.9 capacity. The first question asks is 1 and 2. So let's calculate that. First, as here we have the power factor and the total active power, we can determine what is the value of the complex power of one of these loads. Because as this is the total active power, we can divide that total active power expressed in watts by 3, because the total active power means the power of the loads connected in these 3 phases, and we want 1/3 of that value. As the power factor is 1, we know that we don't have a reactive component in the apparent power. So the reactive component is 0. So this is the complex power in voltamps. This is the same, 1000 plus 0 voltamps. Now that we have the complex power would be the product of the voltage here multiplied by the current here. Let's first name the currents in the sides of the delta. We are going to suppose this sense for the currents in the delta, and we are going to call this current I1, this current I2, and this current I3. These are the currents, the phase currents in the sides of the delta. Now that we have the currents in the sides of the delta and we have the complex power, this formula should be accomplished. The voltage in this side of the delta, A prime, B prime, multiplied by the conjugate of current 1 should be equal to the complex power S1. Then we need to calculate the value of the voltage I prime, B prime. That would be the same as voltage A prime minus voltage B prime, and they coincide respectively with points A and B. So that is voltage A minus voltage B. Here, at the beginning of the problem, we have the values of the phase voltages there. So we have to introduce the values there. So 230 0 minus 230 minus 120 volts, 430 degrees volts. Now that we have done this, we can solve here in this expression. Current I1 would be the complex power divided by that voltage. So then the conjugate of current 1 would be the apparent power divided by the voltage, the line voltage here. And that gives a result of 25 minus 30 amps. Remember that this is the conjugate of the current. So, to get the current, you have to change the sign of the angle. So this is the current that flows through this side of the delta and passes through this load. If we apply the Ohm's law to that load here, we will have that voltage AB prime would be the same as current 1 multiplied by impedance 1. So as they ask the value of impedance 1, we can divide this voltage by this current. So 430 degrees divided by 25, 30 amps. Our result of 16 ohms. So with that, we have obtained the impedance of this load in delta connection. Now that we have obtained set 1, let's do the same with set 2. In this case, what we have is that the active power is 500 watts and the power factor is 0.9 capacity. That is the active power of one of these loads. So then, as you can understand, we can express the complex power because we know several things about the power channel. We know that here we have 500 watts. Here we have an angle which is arc cosine of 0.9, and then we can calculate the value of the reactive power. The tangent of the angle would be the reactive power divided by 500 watts. So the reactive power would be 500 multiplied by the tangent of the arc cosine of 0.9, which gives a result of 242.16 volt-ampere reactive. That means that here in the power we can write the values that we have obtained. When this is capacitive, that means that this generates reactive power. So then we need to introduce the reactive power with a negative sign. So here we have the complex power of one of these loads. What is the next step now? Well, we can use the formula for the complex power and apply that formula to one of these loads. In particular, let's call this current I1 prime, this current here I2 prime, and this current here I3 prime. So then, if we apply the formula of the complex power to, for example, this load, we will have that S2 is the product of. What is the voltage for the difference in potential for this load? Okay, this load is connected between A and the neutral. So then we have voltage UA, phase voltage UA. So phase voltage UA here at this point, here we have the neutral and here we have point A, multiplied by the conjugate of I1 prime, which is this current here. As we already know the voltage and the power, we can get the value of the conjugate of I1 prime, which would be the apparent power, which would be the complex power divided by the phase voltage. That is, this complex power could be expressed in polar notation as 555.56 minus 25.84 volt-amps. So there, you can introduce that in polar form in this expression here. And you can divide by the phase voltage, which was 213.0, and then the conjugate of I prime would be 2.415 minus 25.84 amps. Now that we have this current, its conjugate would be the current that flows through this load here, and that conjugate would be obtained by changing the angle here. So now we have the current flowing through this load. What is the next step now? We need to apply the Ohm's law to this load here. So Z2, the impedance, would be the voltage divided by I1 prime. So the voltage, 230 volts, divided by this current here, 2.415, 25.84 amps. That gives a value for the impedance equal to 95.22 minus 25.84 ohms. And with that, you have obtained the values for both impedances 1 and 2. After this calculation, the next question asks the line currents IA, IB, and IC. So how could we get these values? Well, as you can understand, the current IA, which is flowing here, is going to be divided into two currents. IA1, which is going to supply this delta, and IA2, which is going to be exactly the same as the value that we have already calculated. So, as you can imagine, IA would be equal to this sum, where this value is the same that we have already calculated. So now, as you can understand, our purpose will be to obtain this current here. How could you obtain that current here? Well, if you go to this node and you apply the first Kirchhoff's law to that node, you will have that the current entering here and entering here to that node, the sum of both currents entering should be the same as the current which is flowing here out of the node. So what do we already have from this? We can solve for this current that we don't know, and we will have I1 minus I3. If you remember, we have already calculated I1 in the first question of this problem, so we still need to obtain I3. I3 could be obtained by dividing the apparent power by the voltages by this side of the delta, which is C prime A prime, U C prime A prime. So here we need to calculate this line voltage. How do we calculate this line voltage? By calculating the difference between these phase voltages, which are 230, 120 minus here 230, 0. 400, 115 volts. So there you can introduce here the complex power for this load, which was given in the statement, and we calculated the value for one of the loads in question A, that was 10,000 divided by this voltage here, which is 400, 150. So the conjugate of current 3 will be 25 minus 150 amps. That is the conjugate of the current. So current 3, we can calculate current 3 by changing the sign of this envelope. So we will have this expressed in amps. So now we have current 1 and current 3. So then we can get the value of current A1. Current A1 is the difference between current I1 and current I3. So that gives a result of 43.30 degrees in amps. So now we have current A1. After we have current A1, we can get directly current IA, because it will be the sum of current I1 and current I2. So the sum of both will be, in binomial notation, approximately this, which is equal to 45.48, 1.32 amps. So now that we have the line current expressed in polar and binomial notation, which was line current A, how could we calculate line currents B and C? Well, it is easy. All of us, we know that the three line currents, if the system is a balanced load, as we have in this case, they are shifted an angle of 120 degrees. So, what would be IB? IB is going to be the same absolute value, and here 1.32 minus 120 degrees gives 45.48 minus 118.68 amps. And what about IC? IC should have the same absolute value as the other line currents, and here we should sum an angle of 120. So that gives a result of 121.32 degrees. So these are the three line currents that they asked in question B. In question C, they ask the total complex power of all this assembly. So in this case, we need to sum the total complex power of this load in delta connection plus the total complex power of this load in a star connection. So the total complex power here was 30,000 watts plus the total complex power here would be 3 times the complex power that we had calculated in the first question. If we sum both, we are going to get to this result. And this is the total complex power. As they also ask the total active power, that would be 31,500 watts, and the total reactive power would be 726.48 voltamperes reactive. In question C, they ask about the Aaron connection, and they ask about the two measurements that would be obtained by the two wattmeters that you have in the figure, in the notes, okay? So what you need to do is very easy. You need to write the expressions for Aaron connection for the measured active power, the two wattmeters, whose sum should be the total active power of the whole assembly, and a square root of the difference between the active powers should be the total reactive power in the assembly. Remember that you have the demonstration of these formulas in your notes in lesson 2. Then you have these two equations, and you only need to solve them for P1 and P2. And the results that you are going to have if you solve these equations are going to be these ones. So with that, we have solved all the questions that we had in example 3 of lesson 2.